Welcome you all to the NPTEL online course on Smart Grid, and today we will focus on a topic titled energy management. If you remember my previous lectures on demand side management as well as demand response, where we have discussed in depth how my load curve can be made flatten by taking advantage of the presence of smart grid. Perhaps I can control the energy scenario of my smart grid such that the load curve experienced by the utility can be made flatten. And then further we have entered to another topic called demand response, where the consumers participate in that activity and share their message through aggregator to the utility further, so that the aggregator demands or take observation from the consumer if we are willing to participate in demand response activity, and accordingly the aggregator design the new load curve which is more economical or efficient. Now, with this fundamental theoretical concept, now we are moving towards a DC microgrid energy management scenario, where a demand response activity can be executed within the DC microgrid to support the grid, whether it is at peak load condition or is it at off peak load condition, or sometime the grid is not there. So, dear friends, now it is time for all of us to understand, if the microgrid is connected to my distribution system and hence to the utility, but if the utility is really struggling with the peak requirement of the consumers at large at system level, then the DC microgrid can perhaps adjust its energy scenario such that instead of drawing maximum power from the grid, it can reduce its maximum power from the grid. If it is at off peak, it will try to get as maximum as possible from the grid, but making sure the peak is not shifted to another hour. And the third one, when the grid is not available, it will redesign its demand response activity in such a manner by curtailing some of the non-important loads, so that the energy can be balanced. Let us move step by step how this energy management can be achieved within a DC microgrid, so that the system can operate efficiently with the grid during peak condition, during off peak condition, and also for the worst scenario when the grid is not present. Now, first of all, why there is a lot of challenge for demand response, demand management, energy management, why we are so conservative? The present impact for conventional generation stressed the carbon free energy scenario or the generation around the globe. We are going for energy without making a lot of carbon. Renewable generation is at the top interest of most of the country due to increase in per capita energy consumption and deficiency of fossil fuel. Now, what happens, because the per capita consumption is keep on increasing, and hence we need to meet the expectations of consumers, and it is very difficult for me to establish a huge power plant like super thermal or hydro within 2-3 years time, and hence the quicker solution could be put a lot of renewable into the system. So, that will meet two of my things. One is green energy, and the second, quickly you can meet the expectations or the per capita requirement of the consumers. Now, evolution of semiconductor technology increased utilization of electronics in many fields such as automotive, power, control, etc. That also forced me to go for such kind of DC grids, and DC grids are researched again due to simple control, efficient and direct supply to the load compared to the counterparts available. So, in general what we are arguing here, a smart grid is a must, renewable energy is must, and certainly a DC microgrid will be a better option. Now, we have seen a couple of times with the architecture of DC microgrid, and this is a very simple DC microgrid architecture. I am not going to take a lot of time here because we are all aware we have a single grid connected from the utility side, which is DC grid, then we have DC loads and DC generations. Now, grid interactive DC microgrid system comprises of PV connected to DC microgrid through unidirectional boost converters. Grid side converter GSC is connected between the utility and DC microgrid through a transformer for transmitting the power to a conventional grid and vice versa. Lead acid battery and ultra capacitors are considered as a storage system. Loads are categorized into two types. One is my essential load and the other one is non-essential load. Now, the control schemes, this is a very standard control schemes which is in place, and perhaps we can go for the inner control loops for battery, ultra capacitor, GSC control and PVs. Now, battery and ultra capacitor inner loops. Now, the PFCS, that is power flow control strategy, we could see the power flow control strategy where it extracts the reference current based on operating modes and fed to inner current control loops. The PI controllers provide the duty ratio as output which governs the input current of battery as well as ultra capacitor. Now, in case of GSC control loops, the GSC control loop receives the reference from PFCS and operate accordingly based on its mode. Actual reference value for GSC is synthesized by multiplying unity template generated through phase locked loop, that is PLL, with IGREF, which is tracked by grid input current IG through hysteresis controller. Now, the PV inner control loop, PV is always operated at its maximum power condition except in isolated mode, with surplus power and battery being fully charged conditions where PV shifts into bus regulation. That means, all the time we want our PV to operate its MPPT until unless the battery is fully charged or maybe the grid is not available, etc. MPP, that is MPPT method, provides reference voltage VPREF, which is tracked by the PV source voltage VPB through PI controller, and its output produce required duty ratio DPV. Now, the power flow control strategy, what are the main features? First of all, using power flow control strategy, we can reduce the peak demand, smooth transition between different mode of operation, effective control and management, reduces stress on the battery because it is a smooth transition, increase life of the storage systems because you allow the storage to charge as well as discharge depending upon its SOC level, covering grid connected and islanded mode. That means your system can operate whether the grid is there, even it operates without the grid. Unity power factor feeding to and drawing from conventional grid means the very important fight when the grid, you feed power and you draw power from the conventional grid only through DC microgrid along with unity power factor only. Now, let us see the power flow control strategy which has been proposed in this talk today. Let us start from this point. This is my grid, and the grid, there are two scenarios. The grid may be available to me and sometimes the grid may not be available to me. Now, let us say if the grid is available, then I move this way. If the grid is not available, then I will follow the other loop. Grid is not available means islanded operation. If the grid is available, then it is either peak or off peak. So, when the grid is available to me, check whether it is peak hour. If it is peak hour, then we will check the P from the generation, real power generation from the PV, whether the PV is more than the P load or not. I do repeat, check whether the grid is available. If the grid is available, check whether it is peak hour or not. If it is peak hour, then you can check whether the power from the PV is more than P load or not. Now, when the power is more than the P load, then you check whether the state of charge of the battery is greater than 70% or not. If it is 70%, then you come to this point where you operate at full load, and PV also you allow it MPPP, but do not charge your battery, the storage is no more required. But if it is not charged, then you operate the grid and the battery is still absent, the PV is at MPP operation and load is at full load. I do repeat, if the storage is more than 70% for you and it is at peak hours, and the PV is also greater than PL, so then certainly it is my role to support my grid. So, I can perhaps give that excess energy available to me to the grid, because grid is struggling with peak hours and I can support it. But if it is not, the PV is not enough to meet the load, and if the battery is also at less than 30%, so that case if it is not 30%, then the grid will be disconnected, or it can be connected, but the battery will be supporting my supercapacitor and the PV can operate at MPP and load can also operate at full load. Before we proceed, let us quickly understand the acronyms. B for battery, UC for ultra capacitor, L for load and FL for full load, EL for essential load, NEL for non-essential load, NL for no load. I means ideal, that means when I say I or disk means it could be ideal or disconnected. ABS means it is the battery is observing, and ABS means it is observing, SUP means it is supplying, and BR means this is DC bus regulation. Now, just quickly I will just go back once again. Now, check whether the grid is available or not. If it is available, check whether it is at peak hour. If it is at peak hour, then check whether the PV output from the solar is more than the load or not. If it is yes, check the SOC condition. If it is 70%, then you make your grid observe all the energy which is excess available to you, because the PV is more than PL and the storage is also full. So, the grid can observe the power from my DC grid, the main grid can observe power from the main grid. And the second one, whether you can connect it to this, whether you disconnect it or keep it ideal, it is one of the options available to us. And then the PV can be at MPP and load can be at full load. Similarly, if it is not there, then what we can show that if it is not so, the SOC is not more than 70, then we can allow your battery to observe, and the grid could be ideal or it could be disconnected, and the PV at MPP and load will be at full load only, because locally you have to manage at any cost. Now, if the PV is not greater than PL, it is not more than PL, and then you check whether your SOC is less than, if it is 30, and if it is no, then the grid could be ideal or disconnected, and the battery has to supply, because your generation is low to meet your own grid, and the battery has to supply, and the PV will be at MPP no doubt, and load could be at full load. Now, let us say that it is not at peak hour. If it is not at peak hour, that it is off peak, so certainly I can take my energy from the grid, and then I move from this point to this point. So, here I check whether my PV is greater than my load or not, and if it is not and the SOC is less than 60, then I make sure the grid will be ideal or disconnected, and the battery will be supplying, and the PV will be at MPP and load will be at full load. Now, if it is less than 60, then the grid will be supplying, battery will be observing, PV will be at MPP and load will be at full load. So, first of all you have to meet your own load and then you can support. But the condition here, if the grid is at peak point, then you try to discharge your batteries and allow your grid to observe, and the grid is at off peak, then you do not allow your grid to observe, whereas you take from the grid is supplying power to my DC grid if the battery is not fully charged. So, this algorithm repetitively will help you all the scenario, how do you manage your grid so that the overall load of the system can be maintained. Now, one more important, when let us say if the grid is not available, which is the islanded grid is not available to me, and then you check whether the PV is greater than PL, okay, grid is not there, but PV is more, that means you have more generation from your load and grid is not there. So, what you will do with that? So, if it is yes, and then you check my battery, if it is also fully charged, then the battery will be ideal or disconnected and PV will be off MPP. Now, if the grid is not available and you have excess energy and the battery is also full charged, so then I have to derate my PV, which will not allow my PV to operate at MPP. I have to lower down my PV capacity to make the energy balance within this. Now, if it is not, if the PV is not greater than PL and the SOC is also less than 30, and then I come down to this scenario because the battery is low, and then the SOC is less than 20, then if it is not, then I allow my battery to supply PV at MPP, and I will have one essential load and one non-essential load, and if the battery is still less than 10%, and then I will just go for only non-essential loads, and if it is not less than 9, then I will cater my essential load. So, the conclusion here, if the SOC is less than 20 under off grid, the grid is not connected, and if it is not less than 20, then certainly the battery can supply PV at MPP and I can cater my essential load and non-essential load. But if it is less than 10, then I will certainly take care of my essential load only. Okay. And if it is less than 10, then there is no load that I can cater, means I do not have grid and my PV is also not greater than P load, and my batteries also do not have my energy. So, then finally I have to keep on curtailing the non-essential loads, and finally I will come to a condition where there is no load or the grid is not there, my microgrid is also not able to meet the basic loads. So, this is the whole scenario of the control strategy which has been incorporated. Now, there are different operational modes. If you look into the peak hour mode, in this mode the priority is either to supply the grid or draw minimum power required for essential loads in grid interactive DC microgrid by ensuring DC bus voltage within its limit. Now, in case of off peak hours, conventional grid is now able to deliver enough power at low cost. Charging of battery is preferred along with full load supply from the grid, so that the stored power can be utilized locally when there is peak. That means, if the system is at off peak, we can take power from the grid, charge your battery, and that can be discharged during the peak hour experience of the main grid. So, the local load can be managed by its storage scheme instead of taking energy from the main grid. However, the conventional grid should not be driven into a peak, means if you charge all your battery during off peak, it may so happen that the grid may experience a peak hour. So, that should be avoided. So, you had a peak and you have an off peak, you keep on charging your storage, so that off peak hour goes to another peak which is not desirable. Now, in case of isolated mode of operation, this mode comes into picture when the conventional grid encounters failure or outage. In this mode, DC microgrid operated under all worst scenario like generation become lesser than the load demand with SOC is at critically low and excess generation with battery at high SOCs. Load shedding is done in the first scenario and PV converters will be operated at off MPP in the second scenario. That means if your battery is fully charged, grid is not there, PV is more than load, then you have to go for a off MPP scenario to balance your energy. Now, there are a couple of simulation scenarios. So, we have taken a small DC microgrid. So, simulation is carried out on grid interactive DC microgrid system, which is implemented in real time digital simulator, that is RTDS, and the system is quite small. So, the PV model is 250 watt power and the capacity is 20 ampere hour for the battery, and nominal voltage is 12 volt, and we had two batteries, ultra capacitor 16 volt 58 farad 170 ampere, and the DC link voltage was 48 volts, and the DC load which was 23 ohm, and the annual resistance which is of 46 ohm, and the voltage, utility voltage considered to be 230 VRMS at 50 hertz. And then these are the control parameters being chosen for battery, ultra capacitor, PV and outer voltage loop. Now, the proposed PFCS is explored under all operating scenarios including variation in renewable power and fault outage in the conventional grid. Assessment of PFCS are split into three major categories. Initial two modes cover peak hours and off peak hour mode, and during utility connected conditions whether other will be in islanded conditions. So, we take utility connected, peak and off peak, and then we have islanded conditions where the grid is not present. This is a very simple scenario. So, we have taken different cases at T1, T2, T3, T4, T5, and this scenario is mainly for your T1 in specific, and this is for T5, and you could see that the SOC characteristic, this is irradiation, and you can see the SOC characteristics which is keep on changing, and the voltage of the bus which is at 48 SAR 48, this is for your information, and the current which is the PV current which is dropping at T2 with different cases, and the current of the battery which is increasing and further decreasing, means it started charging and then discharging. And whereas this ultra capacitor current smaller variation, then we look at the load. We had a load earlier and the load is keep on reducing. So, essentially when the load is keep on dropping, we could see the different scenarios from the PV as well as from the batteries, and this is my voltage of the grid and the current of the grid, and these are all closed scenarios of both T1 and T5, and they are the zoomed characteristics at T1 and at T5, means the initial time and the ending time. Now, during the peak hour mode, we have considered different conditions, and based on operation, case 1 where we say PV is greater than PL and SOC is greater than 70, and second case we say PV is greater than PL and the SOC is less than 70. We consider the case 3 where PV is greater than less than PL, PV is less than PL and SOC is greater than 30, and then we had the fourth condition where PV is less than PL and SOC is less than 30. So, we have taken in brief two major scenarios. My PV output is more than load or less than load, and the battery condition whether it is more than 70 or less than 70 or more than 30 or less than 30. So those scenarios have been captured and the energy management has been performed during peak hour. So when you move to the off-peak hours, we can see the scenarios where we could see the voltage bus, which is very close to 48, excluding couple of variations. This is my PV current and this is my battery current variations, and these are the Joule structures for your ultracapacitor current, load current, and almost the same 1, 2, 3, 4, 5, 6, 7, 8, 9 characteristics, but here we have separated out the last 4. Now during off-peak powers also we have considered a few cases. The case 1 where the PV is greater than PL and the SOC is greater than 90%. The case 2 where PV is greater than PL and the SOC is less than 90, and case 3 where the PV is less than PL but the SOC is greater than 60%, and PV is less than PL where the SOC is less than 60%. So you may be surprising why 90, 60, 70, 30 have been considered. So they are based on the existing expertise, but they can certainly vary depending upon the size of the battery and given loading conditions. Isolated mode, when you move to isolated mode, and we can see that this is my load scenario, and then this is the SOC scenario and B bus, which is again with minor variation, and you can see the current for the PV which is varying, and then this is my battery current characteristic, and finally my ultracapacitor, and this is a superimposed characteristics where the power from the PV and power during MPP and the load current, ultracapacitor power and power from the battery all have been simultaneously captured. Now they are the actually voltage characteristic slightly zoomed, and then IPV, I battery, I ultracapacitor, B bus, IPV, I battery and I ultracapacitor. So as a whole, if you see the energy management scenario, the control strategy is very smooth, and we are able to balance the available energy along with my storage energy available to meet out the existing loads, even both grid connected and without grid, during both peak and off peak hours when the grid is existing. So we try to manage the energy in such a manner so the peak and off peak scenario of the grid existence duration will be met successfully. Now in case of isolated mode, we have considered like PV whether it is greater than PL when the SOC is greater than 90, and then we have case number 2 where PV is greater than PL and the SOC is less than 95%. Then we have case number 3 where PV is less than PL and the SOC is greater than 30%, and then we have PV less than PL and the SOC is less than 30%. So once again different scenarios have been discussed. So to conclude, a simplified power flow control strategy is proposed for minimizing the peak demand as well as ensuring optimal utilization of renewable energy and storage. So what has been concluded? Now whether you have grid, when you have the grid, it may be available, it may not be available. Under both the circumstances, my microgrid has to balance its energy by optimally utilizing its own resources from the PV and the storage which is available to. Now a low voltage DC microgrid was modeled by enclosing a PV source, hybrid storage system and load to validate the concept of PFCS. Now the performance of the developed strategy is explored under various practical conditions to ensure reliable and efficient operation of a DC microgrid. The simulation results were satisfactory and the grid remained stable even in case of extreme conditions. The grid was stable even under extreme conditions. Peak demand minimization, diminishing of stress on the conventional grid network, pervasive control analysis, fast regulation of bus voltage, flawless transfer between modes, unity power factor supplying and observing by the conventional grid are observed as the main feature of this case study. Thank you.